In Unit 8, we're going to be studying two sample t-tests. First, we're going to be looking at a dependent t-test. Now, remember that in Unit 7, we looked at one sample t-test. We know that a t-test itself is when you are analyzing the mean of a population. So here we're going to be looking at means. In this first segment, we are specifically going to be looking at dependent t-tests. Now, dependent just means that you're taking two samples, right, and one sample depends on the other. So think of this kind of like a before and after scenario where maybe you want to track people's GPAs. Maybe you want to know if students' GPAs improve from their freshman year to their senior year. And so you would go person by person and see what the difference is in person number one from their freshman year to their senior year, person number two, what's the difference from their freshman year to their senior year. So you're analyzing the difference in each pair and then collecting those differences together to see if there is truly a significant difference or not. Okay, now null hypothesis, you're always going to go in under the impression that there is no difference whatsoever. So in our example, we're going to assume that GPAs stay the same from your freshman year to the senior year. So we're going to assume that there's no difference. The way that you would write that is that the mean difference is 0. You'll also see the fancy kind of letter D. It's the Greek symbol for sigma. This is the lowercase symbol to represent the difference of the entire population. And then, of course, your alternative hypothesis, we are trying to prove that there actually is a difference. A lot of times we're just trying to prove in general that there's a difference, but sometimes we may be trying to prove that one of these treatments is better than the other, or that one of these treatments is worse than the other. Maybe you're trying to prove that GPAs go up from your freshman year to your senior year, or maybe you try to prove that GPAs actually drop from your freshman year to your senior year. Okay, let's take a look at an example here. So researchers designed an experiment to study the effects of caffeine withdrawal. Each subject took a depression test after 2 days of taking a capsule containing their normal caffeine intake, and again 2 days after taking a caffeine-free placebo. The order of the treatments was randomized. All right, so over here we have a chart. We see that we have 11 subjects. Each of them was measured for their depression symptoms with caffeine and without caffeine. That's what makes this a dependent t-test. Their level of depression depends on the person. Take a look at subject number 10 and subject number 11. I wouldn't want to compare subject number 10 with caffeine to subject number 11 without caffeine, because these are clearly two very different people. If you look at the rest of subject number 10, they just have very high depression levels in general with or without caffeine. And person number 11, they have very low depression levels with or without caffeine. So with a dependent sample, this is where you're measuring two things on the same person. Oftentimes it's a before and after situation. In this case, it's like a with or without situation, with caffeine versus without caffeine. And you want to look at those differences for each person individually before you start running the data. So what we're going to do is we are going to come over here to our third column, and we're going to find the difference in depression levels for each person. And it specifically says here that we're going to do placebo minus caffeine. Now, a placebo is a fake treatment. So when these people are doing the test, it's considered to be a blind experiment. The subjects are blinded from which type of capsule they're getting. Now, they're not blindfolded. It's just that the two pills look the same. Like one of the capsules actually has caffeine in it, but the other capsule is identical and it doesn't have any caffeine in it. So it prevents them from getting thoughts of, oh, I'm not getting my caffeine, I just feel more depressed now. So having that blinded test allows for more realistic data here. Okay, so let's go through here and calculate the differences. So placebo minus caffeine. So for the subject number 1, we're going to do 6 minus 5. We get a positive 1. So a positive number indicates that they were more depressed with the placebo. So they were more depressed when you took their caffeine away. Person number 2, placebo minus caffeine, 11 minus 5 is 6. Person number 3, 5 minus 4 is 1. Person number 4, 7 minus 3 is 4. Person number 5, 6 minus 8 is -2. Now this is our first negative number. Notice here that a negative number indicates that this person was actually less depressed when they removed their caffeine intake. Person number 6, we've got 9 minus 5 is 4. Subject number 7, 4 minus 0 is 4. Person number 8, 3 minus 0 is 3. Person number 9, 2 minus 2 is 0. Notice that a difference of 0 means that there's not any difference at all. This person scored the same with caffeine as they did without caffeine. Subject number 10, 12 minus 11 is 1. And subject number 11, 0 minus 1 is -1. So there we have another negative number, which indicates that their depression levels actually went down when they took the placebo. Now, at first glance here, I see a lot more positive numbers than I do negative numbers. And positive numbers reflect that their depression levels were higher when you removed their caffeine. So my first instinct is to say that depression increases when you remove a person's caffeine, but I don't know that for sure. That's why we're actually running the test. So we need to calculate some statistics here. We need to calculate the mean and the standard deviation. So what we're going to do is we're going to go through in our calculator and we're going to type this data in. So remember, in your calculator, what you're going to do, you're going to push the stat button, and then number 1 where it says edit, you're going to go type in the data. Not all of the data, just row 3, because we only care about what the difference is for each one of these people. We don't care about what their score was with caffeine or what their score was without caffeine. We only care about how much it changed. Okay, so once you go type that in, we need to calculate our statistics. So you'll go back to the stat button again, and you're going to go over, use your over arrow to go to calc, which stands for calculate, and you're going to select number 1 there. You're going to select 1 var stats. That's what's going to give you the mean and the standard deviation. So I would recommend pausing the video at this point so that you can get this data typed into your calculator and run these numbers for yourself. Alright, so after number crunching, I see the mean at the top. Remember, the symbol for mean is X bar. Symbol for mean is X bar, so we've got X bar equals 1.91. And the standard deviation, make sure you use the appropriate standard deviation, which is the S symbol, is 2.47. Okay? So we're going to be able to use this information here to determine whether this data provides sufficient evidence to conclude that being deprived of caffeine impacts depression. So let's carry out our test. So remember, the first step of this test, we're going to have to write down our hypothesis. Our null hypothesis is that there is no difference whatsoever. So I'm going to use that fancy symbol, which just means, like, that's kind of like a fancy letter D. It means that there's no difference. And we're trying to see whether or not being deprived of caffeine impacts depression. We're not specifically trying to prove that caffeine deprivation lowers depression. We're not specifically trying to prove that caffeine deprivation increases depression. We're just trying to see if it impacts it whatsoever. So I'm going to do that the difference is not equal to 0. Now, like usual, we're going to have to calculate our critical value, or not calculate it, we just need to go look it up. So critical value is based on 2 things, your significance level and your degrees of freedom. Since this is a 2-sided test, I'm going to be shading both ends of my t-distribution. So if my alpha level is 0.01, that's going to be split in half. So the sides have to add up to 0.01. So this is going to be 0.005 on either end. It's also based on degrees of freedom, which we know is n minus 1. We have 11 subjects in this study, so my degrees of freedom is going to be 10. So I'm going to pull up my t-chart over here, and I'm going to look up my critical value on my t-table. I'm looking at an upper tail probability of 0.005 with 10 degrees of freedom. And I'm getting a critical value of 3.169, plus or minus 3.169. And the reason why I say plus or minus here is because you have either end shaded. You have the negative side shaded as well as the positive side, so it could be on either end. All right, shifting gears now to some calculations, we're going to calculate our test statistic. This is the formula that you see on your formula chart. The little D bar right here, remember, like X bar is the mean. D bar just means the mean difference. So the mean that we calculated earlier, that is the difference, the average difference that we collected from our sample. So that's what's going to go on top here. So this is going to be 1.1. Okay, minus sigma. Notice this symbol is the same symbol that we used in our null hypothesis. Well, you're assuming that there's no difference whatsoever, so you put a 0 there. That's just the value from your null hypothesis. On the bottom, we have the standard error. We calculate standard error the same way that we did in the previous unit. You're going to take your standard deviation, 2.47, over the square root of our sample size, so over the square root of 11. And if we crunch these numbers here, I'm getting a test statistic of 2.56. Now remember on your chart, those cutoffs, what's shaded in red is 3.169. And we know the t-distribution is symmetric, 0 is in the middle. So if this is 0.169 right here, then 2.56 would be somewhere in the middle. Notice it's not in the shaded region. It's not in the shaded region. That shaded region is called the rejection region. You only reject the null hypothesis if your test statistic falls in that shaded region. So in this case, we would fail to reject the null hypothesis, which means we cannot conclude that being deprived of caffeine impacts depression. All right, now just a follow-up of that, we're going to practice doing a confidence interval as well. For the same exact problem, we are going to construct a 99% confidence interval for the mean average difference in depression scores with and without caffeine. And we want to make sure that the numbers that we get here support the conclusion that we made in part A, which was that we failed to reject the null hypothesis, and we said that we cannot conclude that caffeine deprivation impacts depression. All right, so let's set off here. X bar on your formula chart, you might also see that written as D bar, which just stands for difference. The bar still represents the mean though, so that's going to be 1.91 plus or minus your t critical value. Now keep in mind that this is a confidence interval, a 99% confidence interval. Confidence interval is always centered in the middle, so if this is a 99% confidence interval, I'm going to draw my t distribution with 99% in the middle. So if I'm looking at the outside, it's 1% split in half, so that would be 0.005 on either side. Okay, and there are still 11 subjects here, which means we have 10 degrees of freedom. So for my critical value, that critical value has to match that 99%. So we're looking at an upper tail probability of 0.005. So just like we looked up the critical value on our chart last time, we're looking at the same critical value here. So I'm going to go to 10 degrees of freedom. and I'm looking at 0.005 for my upper tail probability. That's 3.169. Standard error is the same formula that we calculated on the previous page. That's where we do 2.47 over the square root of 10. I'm sorry, over the square root of 11 because our sample size is 11. All right, then we're going to do some computations here. I'm going to get my calculator out, and we're going to calculate this part right here. Now, there is a name for this. This calculation here where you multiply the critical value times the standard error is called margin of error. So like right now, our best guess at the true difference is this mean that we calculated from our sample. The margin of error tells you how far off we expect that mean to be based on all possible samples of 11 subjects. All right, so we're going to calculate this here, 3.169 times 2.47 over the square root of 11. This gives me a margin of error of 2.36. Now I'm going to calculate the interval itself. On the low end, I do 1.91 minus 2.36. This is going to give me the low end of negative 0.45. And on the high end, I'm going to do 1.91 plus 2.36. Gives me 4.27. Keep in mind what our confidence interval is. Confidence interval is the interval that is thought to contain the true difference between their depression levels with caffeine and their depression levels without caffeine. Well, notice negative number. Remember, negative number we said meant that the person, that taking away their caffeine lowered their depression. And on the upper end, we see a positive number. Remember, we said that a positive number indicates that taking away their caffeine increased their depression. And of course, what number falls right between negatives and positives? 0. And 0 would represent no difference at all. So remember how when we create our conclusion from our hypothesis test, how we use very vague wording here. We fail to reject the null hypothesis. We say there is not enough evidence to conclude that caffeine deprivation impacts depression. This is why we use vague wording, because we can't actually tell what's happening when we take away the caffeine. On one end, maybe their depression is going to lower. On the other end, maybe their depression is going to increase. Or maybe their depression level stays exactly the same when you take away their caffeine. We have no conclusion because there are a multitude of options here.